Gold and diamonds are two of the most well-known expensive materials on Earth. Their value comes from a combination of rarity, beauty, and utility. Gold has been treasured for thousands of years, perfect for jewelry and currency due to its rarity and non-tarnishing nature. Its unique properties, like being a great conductor of electricity, also give it practical uses in electronics. Diamonds, formed under extreme pressure and heat, are highly sought after for their sparkle and hardness. The difficult and dangerous mining process adds to their high cost. Additionally, diamonds have industrial uses because they are the hardest natural material known. Both gold and diamonds have maintained their value over centuries, considered safe investments. Despite their high costs, gold and diamonds are not the most expensive substances in the world. There is something far more costly and rare: antimatter. Antimatter is the most expensive material in the world, making gold and diamonds look cheap in comparison. It is a type of matter with the opposite charge to the normal matter we know. 1 gram of antimatter could cost around $62.5 trillion due to the extreme difficulty of producing and storing it. Unlike gold or diamonds, antimatter must be created in a laboratory, involving advanced technology and immense energy. Though it sounds like science fiction, antimatter is real and crucial in modern physics. Scientists study antimatter to understand the fundamental laws of the universe. The costs involved in antimatter research are justified by the potential scientific breakthroughs. Before we delve into its applications, let's first understand what antimatter really is. Antimatter is essentially the mirror image of normal matter, with each particle having a corresponding antiparticle of opposite charge. For example, the antiparticle of an electron is a positron. When matter and antimatter come into contact, they annihilate each other, releasing a huge amount of energy. This process, called annihilation, produces energy many times greater than nuclear reactions. Creating antimatter involves particle accelerators, which speed up particles to high speeds and smash them together. The amount of antimatter produced is incredibly tiny. Storing antimatter is another challenge. It must be kept in a vacuum and suspended using magnetic fields. This makes the storage process extremely complicated and costly. Despite these challenges, the potential power of antimatter is immense. Antimatter has several unique properties, including its opposite charge. For instance, while protons have a positive charge, antiprotons have a negative charge. The annihilation process converts matter and antimatter into pure energy based on Einstein's equation, E = mc squared. This makes antimatter potentially the most efficient energy source known. Antimatter also has implications for our understanding of the universe. During the Big Bang, equal amounts of matter and antimatter were created, but the observable universe is mostly matter. The reason for this imbalance is one of the biggest mysteries in physics. The difficulty in producing and storing antimatter contributes to its high cost. Producing antimatter is incredibly expensive. Facilities like CERN, where antimatter can be produced, cost billions to build and operate. The process is energy-intensive, requiring significant energy to accelerate particles for collisions. The amount of antimatter produced is very small. CERN can produce only a few nanograms per year. Storing antimatter safely requires advanced technology such as magnetic traps and vacuum chambers. These storage methods are costly and require constant maintenance. The limited production and high costs make antimatter the most expensive material in the world. Despite these challenges, research continues due to its potential benefits. Despite its high cost, antimatter has potential uses in science and technology. One promising application is in medicine, such as positron emission tomography, PET scans. PET scans use positrons to create detailed images of the human body, aiding in disease diagnosis. Antimatter could revolutionize space travel due to its high energy density, potentially powering spacecraft for long-distance travel. It could also be used for energy production, providing a nearly limitless power source. However, the cost and difficulty of producing and storing antimatter make these applications currently impractical. Research into antimatter continues, exploring new ways to produce and utilize it. The potential benefits are enormous, but significant challenges remain. Antimatter is not readily available on Earth. It is produced naturally in very small amounts, such as in cosmic rays and certain types of radioactive decay. These natural sources do not provide enough antimatter for practical use. The primary way to obtain antimatter is through particle accelerators, which simulate conditions not naturally found on Earth. This makes antimatter extremely rare and difficult to produce. The technology required to create antimatter is advanced and expensive, limiting its availability. Unlike gold or diamonds, antimatter must be artificially created, requiring significant resources and expertise. The scarcity of production sites further limits the availability of antimatter. Transporting antimatter poses significant risks. Because antimatter annihilates upon contact with normal matter, it must be stored in a way that prevents any interaction. This requires sophisticated magnetic traps and vacuum chambers, which are both expensive and delicate. The annihilation of antimatter and matter releases a huge amount of energy. Even a small amount of antimatter could cause a massive explosion if it came into contact with matter. This makes transporting antimatter extremely dangerous. Due to these risks, transporting antimatter is not currently feasible on a large scale. Research into safer and more efficient methods of storage and transport is ongoing, but significant challenges remain. Antimatter remains the most expensive material in the world. Its high cost is due to the extreme difficulty of producing and storing it. The properties of antimatter, such as its opposite charge and annihilation with matter, make it both fascinating and challenging to work with. Despite its high cost, antimatter has potential uses in medicine, energy, and space travel. However, its rarity on Earth and the risks associated with transporting it pose significant challenges. Current research is focused on finding new ways to produce and utilize antimatter safely and efficiently. While practical applications may still be far off, the potential benefits of antimatter research are enormous. As technology advances, we may one day unlock the full potential of this incredible material.